Alright, so here we are, Falcons. I'm glad you're here. This is our first of our videos over the Christmas break, and we're going to see how many we can get through over the next 3 weeks. And the first one is going to be on the different types of discontinuities that you can have within a function. So if you take a look at the paper we have right here, the first function we have is x squared minus x minus 6 divided by x minus 3. So looking at this rational function, it's clear probably the first thing we should probably try doing is seeing if there's anything we can factor that then might cancel. So obviously the numerator is the one that we could try factoring. So if we did that, well, we're going to get x minus 3 and then x plus 2 over x minus 3. The reason being negative 3 plus 2 is obviously negative 1. Negative 3 times 2 is negative 6. When we look at that, it's pretty clear x minus 3's can cancel. So the only thing I'm left with is x plus 2. However, since there was still a denominator, we are not allowed to divide by anything that would make the denominator 0, which in this case would mean that x minus 3 cannot equal 0. And solving that equation would give us the result of x cannot equal 3. So our function is x plus 2. However, x cannot equal 3. If I was to graph that on a coordinate plane, well, x plus 2 is very simple, linear equation. So x plus 2, the starting point is positive 2. The y-intercept is going to be having a slope of 1 because that's the coefficient of x. So if I go up 1, I'm going to get the point 1, 3. However, remember x cannot equal 3, so at 2 it will be 4, but then at 3 there's going to be what we refer to as a hole in the graph. So if I was to graph it, it's going to go through these points. It's going to keep going in this direction. But this point right here is known as a hole in the graph. The reason why we're talking about this in terms of functions, it is a discontinuity. It's the first type, a hole. It's also known as a removable discontinuity. So we can put that, removable discontinuity. So again, the way you're usually going to get holes in the graph is if you're factoring and the same thing happens to be in the numerator and the denominator. When that cancels, the fact that it existed in the denominator in the first place means that any value that would make the denominator 0 means there's ultimately going to be a hole in the graph where that happened. Alright, so there's the first type, a hole or a removable discontinuity. The next type we're going to be talking about is a jump discontinuity. And a jump discontinuity occurs basically, the most common occurrence is when it's a piecewise function. So if I was to give us the following function and I said x minus 3 is the function when x is less than 2. However, we're going to say that the function is x squared when x is greater than or equal to 2. So if I tried graphing that piecewise function, let's see what happens. Well, basically, x equals 2 is the value that's the most important for this one. So we're going to find out what happens both at x minus 3 and x squared. If I plug in 2 into x minus 3, well, 2 minus 3 is negative 1. So we're going to get a point right here. Also, there was no equal bar, so notice I did put an open circle. If I plug in 2 into x squared, I get 4. And there's going to be a closed circle. All right, the graph actually exists there. It does not exist there. And then since this part, x minus 3, has a slope of positive 1, the graph's going to go off in this direction. And on the other one, this one right here, that's where x is squared, so it's going to take the form of a quadratic, and it's already starting to go up very, very quickly. So that's the jump discontinuity that you can notice right here, is that, as I'm going along this graph to the right, I don't quite reach this point, but that's where I'm intending to go, is at negative 1. However, I have to lift my pen up and go all the way to positive 4, and that's why the graph has a jump, which is, like we said, one of the 3 types of discontinuities. So far we've learned holes in the graphs. We've talked about when those happen. We've talked about jump discontinuities, and when those happen, look, normally it's piecewise functions. The last type we need to talk about are when we have vertical asymptotes. So we'll take a look at that. So vertical asymptotes. Now, vertical asymptotes happen mostly when, unlike holes in the graph, in holes in the graph, two things canceled, one on the numerator and the denominator. For a vertical asymptote, that just means there's an irrational expression that, there's something in the denominator that can equal 0, but it never canceled with something in the numerator. So if I had something like just a basic function, x over x minus 1, well, what value would make the denominator 0? Well, if I said x minus 1 cannot equal 0, then solving it would give us x cannot equal 1. So that's where the vertical asymptote would occur for this particular graph. So if I graphed it, we're going to have a vertical asymptote at 1. And we're not going to spend a whole lot of time on this because you know how to substitute values. But if we substitute in values, we would get 0, 0. And it's going to be going down towards negative infinity in this direction, going off like this. And then on the other side, it's going to be approaching positive infinity as it goes off in this direction there. All right, so that's what the graph would look like. Again, keep in mind, as this graph right here approaches 1, the graph is approaching negative infinity. If I then go from the other side, it's approaching positive infinity. These values are obviously not approaching the same thing, which is why there's a discontinuity there. In this case, it's a vertical asymptote discontinuity. All right, so we've talked about the 3 types of discontinuities you need to be aware of. Now, for your notebook, here's what you guys are going to be doing. Every single day that I make a video, you guys are going to put one problem down on the page. They might be a little on the harder side because it's only one problem, but it's meant to get you guys thinking. It's going to be a lot of times maybe questions we haven't done explicitly, but I want you guys to try your best. I know you guys are more than smart enough and capable of doing them if you put a little effort into them. All right, so the first question I want you guys to tackle is right here. So I'll go over it with you. So again, on a separate sheet of paper. Okay, don't put more than one on the same piece. I want it to be really easy to grade. All right. So it says, your job is to write a rational expression that satisfies the following conditions. It needs to be a third-degree polynomial as a numerator with a second-degree polynomial as the denominator. All right. It says both polynomials must be in standard form. So I put example x to the third plus 3x squared minus 5x plus 8. So since that's the third degree function, that could be the possible numerator. I'm not saying it is or isn't. I'm just saying that's what I want it to look like. All right. The other condition is when graphed, it must go through the points -1, -2, and 3, 10. So I'm giving you 2 points the graph has to go through. And then the final condition, it says the graph can only have 1 point discontinuity on the interval -infinity to infinity, and it must occur at x equals 2. All right, so I want a third degree function over a second degree function that also goes through -1, -2, through 3, 10, and it's only allowed to have 1 point discontinuity, which occurs at x equals 2. Okay, it's not going to have any vertical asymptotes. It's not going to have any jump discontinuities. Okay, it's just going to have 1 point discontinuity at x equals 2. So I am sure you guys can handle that. I wish you guys good luck. All right, and I hope you guys are so far having a great Christmas break. With that, I will see you guys later.